Today I'm going to talk about output analysis for Markov Chain Monte Carlo. I'd like to thank ahead of time Dudica Vatz and Galen Jones, who are co-authors on this work. So the general setting that we're going to be interested in is exploration of a probability distribution, pi, having support on the d-dimensional real line. And we are thinking about D here as being somewhat large to very large, not a toy, 1 or 2. We're going to explore this distribution pi using a Harris-ergodic Markov chain, which we'll call X. And for now, we're going to consider estimating an expectation with respect to pi. For the first half of this talk, we're going to consider this as a univariate expectation. So G, our expectation with respect to G, is going to be a function that maps my state space to the real line. And later on, we'll generalize everything I'm going to talk about into a multivariate target. Well, then it's easy to find a consistent estimator. We can simply use the ergodic average or average over our draws after applying our function G. The strong law of large numbers tells us that as long as the expected value or the expected absolute value of G is finite, then this is going to be a strongly consistent estimator, theta n. And further, under some additional regularity conditions, essentially mixing conditions on the Markov chain, we will have a central limit theorem that basically has this asymptotic variance. This would be sort of our variance of our target plus 2 times the infinite sum of the lag covariances. And this allows us to essentially stop the simulation when the uncertainty is small enough. So as long as I can estimate that asymptotic variance, sigma, I'm going to say I have an estimator of that sigma hat. I'll be a little bit more precise later, but not that careful, because that's not the point here. Then our central limit theorem allows construction of a confidence interval. And that confidence interval is going to have width. The length of that confidence interval is going to be 2 times our critical value times the Monte Carlo standard error. Then I can simulate until I have enough data, until n is large enough that that confidence interval length is less than some pre-specified value, which we'll call epsilon. Okay, this is referred to as a fixed width stopping rule, and it will terminate the simulation the first time that confidence interval length is below our pre-specified epsilon value. So let's just see how this works in very much a toy example, the AR1 model. We have a Markov chain where the current state is rho times the prior state plus some white noise, where that's going to be IID normal 0, 1 for our noise. All right, I have some settings here. I'm going to choose rho to be 0.95, so a moderate level of correlation in this. And I'm going to run until a confidence interval length is less than 0.2. All right, for now, I'll just say that that estimator of the asymptotic variance is calculated using batch means. I'm going to do this after 1,000 draws in the chain. I'm going to check this, and then I'm going to continue to add 1,000 draws until this criteria is met for the first time. And this plot summarizes that simulation study. All right, so on the first iteration, after 1,000 draws, my estimate is negative 0.2. My value here is about 1.8 for the confidence interval length. After that, it's negative 0.5, let's say, and the confidence interval length is more than 1.5. As I simulate, my confidence intervals get smaller and smaller, and I want to simulate until I hit this threshold, this 0.2 value. The first time I do that is about 150,000 draws. And also, the estimate at that point is, well, it's close to 0. That's the black line. We know that is the truth. And it's maybe minus 0.02 in that range. And then I'm satisfied, right? I've estimated my value with with a narrow enough confidence interval that I'm happy, and I can stop my simulation at that approximate 150,000 drops. What we're interested in here are a couple things. Well, first, and we're going to walk through this problem relatively slowly in the univariate case, and then somewhat quickly generalize to the multivariate case, which is much more interesting. So first, we'll think about what requirements are necessary for my confidence for this procedure to be asymptotically valid, and for the resulting confidence intervals to have the right coverage probability. Then we'll look at some improvements, again, from a univariate perspective. We'll think about, does this work in finite sample settings, and extensions to a fixed volume stopping rule, where we actually will be thinking about the multivariate nature of estimation. All right, so we need to be a little bit more precise about fixed width stopping rules. So suppose epsilon is positive, and we're going to consider terminating the simulation when our width of our interval plus some sort of small term, epsilon times an indicator that says don't check until you have n star draws. There's no restrictions on n star, plus 1 over n is less than epsilon. All right, we need these to push the theory through. Given a central limit theorem and a strongly consistent estimator of sigma squared, then this fixed width stopping rule is asymptotically valid. It terminates the simulation with probability 1, and the resulting confidence intervals have the right coverage probability. Now, there's a little bit other piece here that we need. We actually need a functional central limit theorem, but in Markov chain sampling, that tends to hold under the identical conditions that our usual Markov chain central limit theorem holds under. So it's a little bit imprecise in the general setting, but in our setting, this is okay. This is superior to using convergence diagnostics as a stopping criteria. The problem is, if we look at this in multiple dimensions, then a single epsilon is going to be very unlikely to be suitable. And so what do? How do we improve upon this? Well, one thing you could do is do a relative standard deviation fixed width stopping rule. This is very much designed for Bayesian simulation now. So we want to terminate when the computational uncertainty is small relative to the posterior uncertainty. Now, we don't have to measure these with confidence interval length and posterior variance, but that's what we've chosen to present here, and that's sort of, I think, the most natural setup. So let's let lambda squared be the variance of our target function, and we are going to denote that as the posterior variance, and we're going to estimate that in line from the same simulation with lambda hat squared. Okay, usually that's just our sample variance. Then we can terminate the simulation when essentially our confidence interval length is less than an epsilonth fraction of our estimated posterior standard deviation. Now I have the same sort of, restrictions here where, don't check until you have n star, that's a minimum, and a 1 over n term here. Okay, we're thinking about n as large, so this is small, and this is a little bit of a safety feature, really a safety feature to make sure that our estimates of sigma squared and lambda squared are stable. Okay, that's all we're trying to do with this piece here. All right, so essentially we're stopping when our confidence interval length, that's our measure of computational uncertainty, is small relative to our posterior uncertainty as measured by the posterior standard deviation. Given a central limit theorem and strongly consistent estimators of these two quantities, the asymptotic variance and the posterior variance, then this relative standard deviation fixed width stopping rule is asymptotically valid. So what this does is this provides a simple yet informative automated stopping criteria that we can apply now to multiple multivariate settings. It does not require prior knowledge about the magnitude of the parameters. And further, a single epsilon can suffice in multivariate settings. What's really kind of exciting about this piece, though, that I've been advertising for quite a while for this univariate setting, is that it is equivalent to terminating when the effective sample size is sufficiently large. So the connection with effective sample size is as follows. So we define effective sample size as this guy. This is in some ways I would say a standard definition, but you may have seen it defined in terms of sample quantities. And we're going to make a little bit of a distinction here in that we have sort of the true unknown effective sample size, and then we have to estimate the effective sample size. Okay, so we're going to choose to estimate this with strongly consistent estimators like we need in our fixed width stopping rule. Okay, this effective sample size gets thrown around in a variety of different MCMC software packages, and some of those estimators of effective sample size are not that great. So this is sort of, we have stronger, better estimates here. We're gonna consider terminating the simulation when the effective sample size is larger than some threshold value, which we'll call K. Then at termination, our estimated effective sample size is here. And that just with a little bit of rearrangement results in this. And at termination, that quantity is bigger than or equal to K. Well, if I just rewrite that quantity as 4 times whatever critical value squared divided by epsilon squared, then I move my sigma squared to the other side. I take square root of everything. What I get is this is equivalent to terminating when a confidence interval length is less than or equal to epsilon times an estimate of the posterior standard deviation. All right. So this gives me a way to quantify effective sample size. So to achieve a Monte Carlo error that is at most 2% of the posterior standard deviation with 90% confidence, then I need an effective sample size of more than 27,000, which is much larger than most effective sample size. Now, the more exciting part is what can we do when we think about multivariate output analysis for MCMC? Okay, well, the short answer is everything holds, all right? Everything I've described to date, we can do in this setting. So now I have a p-dimensional expectation that I'm trying to estimate. I'm gonna still call that theta, okay? The strong law of large numbers, I still just average over my G applied to my chain, and I get a strongly consistent estimator. And I can establish a multivariate Markov chain central limit theorem. Now, this variance covariance matrix becomes much more complicated, all right? Because it is an infinite sum of a covariance matrix, and it is a little bit challenging to work with this piece. We are going to suppose that we have a strongly consistent estimator of that covariance matrix, that asymptotic covariance matrix. This is available under checkable conditions for batch means, spectral variance estimators, and weighted batch means, which is a new thing that I did with one of my PhD students. So as long as we have a strongly consistent estimator, then we can estimate theta with a confidence region. This is a confidence ellipsoid will take this form. Now, a fixed volume rule terminates when the volume of that region, we'll use the pth root of the volume, is sufficiently small. But here again, we see the same problem. How do we choose epsilon in this setting? And conceptually, that's hard to do. One thing we can do is we can make it relative to something, especially if we're in a Bayesian framework. So let's let capital lambda be our posterior covariance matrix, which is easy to estimate using the sample covariance matrix capital lambda sub n. Then we can stop the simulation the first time our confidence region volume, the pth root of that, is less than an epsilonth fraction of the pth root of our sample covariance matrix. Essentially, what this does is it terminates when the volume of the confidence region is small enough, all right? And a relative volume stopping rule produces an asymptotically valid confidence region, all right? We have asymptotic validity for this. But what this also allows us to do is define a multivariate effective sample size, okay? This takes the same form. All we're doing is we're looking at the pth root of the determinants here. This reduces to the usual univariate effective sample size when p is small. And we can further estimate this with our strongly consistent estimators of capital lambda and capital sigma. Then stopping the first time that we achieve this, where our pth of the pth root of our volume is sufficiently small, this becomes asymptotically equivalent to stopping when your effective sample size is bigger than this threshold. And this is a little bit more of an asymptotic result because we have a chi-squared distribution plugged in here instead. Okay. So now to think about this for, let's say p is 5, a 5-dimensional target, to achieve a Monte Carlo error that is most 2% of the posterior standard deviation with 90% confidence, we require an effective sample size of almost 54,000 draws. Right? So about twice as big as what we had before, but now for a 5-dimensional problem. And we're just going to illustrate that this works in a Bayesian dynamic space-time model. So what's important to note about this model is data, model, sampler is all from the spatial Bayes package. All right, so what we've done is we've taken sort of an off-the-shelf sampler and we've applied our output analysis techniques to it. The reason for that being is to somewhat illustrate that there's nothing special that we need to know about the sampler. Now, we do have restrictions on getting a CLT and these sort of things. We can't check those here, but there's nothing, we're not doing anything special. We're taking data just like anybody else could, taking MCMC data, and now we're doing output analysis on it. So here we're trying to model temperature at specific times and locations, and these are through a particular Bayesian model. All the prior specifications are built into this package, and we're going to consider 10 weather stations in year 2000 and estimate the posterior mean of all the parameters. Now, we're not actually going to do that because visually that many parameters becomes very, very problematic to see. What we're going to do is we're going to show you, what I want to do is show you why this is important. I have a couple things on this plot. The first, I have this blue line here. Okay, this represents if I just calculated marginal confidence intervals with no correction. Okay, so here to here for beta 1 would represent a 90% confidence interval. Here to here for beta 2 represents a marginal 90% confidence interval for that. But notice this area is kind of big. It's going to be a lot bigger than this confidence region, this confidence ellipsoid. It's also incorrect because we're only correct for marginal coverage. So we could do a Bonferroni correction, but then that region becomes even larger. All right. And so that becomes problematic too. And as dimension increases, that becomes even more and more problematic. Now if we look at a confidence ellipsoid here, we can see the high correlation between beta 1 and beta 2, which is not surprising. We also see it between U1 and U2, again, not surprising. These are consecutive data points in time, or consecutive parameters in time from the first month to the second one, okay? And what we're doing is using a multivariate effective sample size, we're effectively capturing this correlation and using that information to our advantage. All right, so just a quick summary. Effective sample size can be used to rigorously terminate an MCMC simulation. All right. We've also given some insight in this series of papers as to what effective sample size means and how we can think about it with regard to computational uncertainty. All the necessary calculations are implemented in the MCMC-SCR package, which is available on CRAN and GitHub, thanks to Dudica. And I also want to mention that this is joint work with Galen Jones, who was my advisor at the University of Minnesota, and Dudica Vats, who's now at IIT Kanpur. Thank you.